Hello, today we'll be talking about our new paper, Vert Attack, which is a new adversarial attack focused on exploiting the disadvantages of current text classifiers. So first, we need to establish what a text classifier does. Simply put, our text classifier is going to take an input text and assign some label to them. In this case, this text classifier might be acting as sentiment classification, so it's taking in text and assigning specific labels. In this case, positive for this middle, neutral for the first, or negative for the third one. Sometimes these classifiers can be used for things like hate speech detection, to monitor websites. In this example here, we have this negative text that this classifier is blocking from allowing to be posted to the website because it's taken and analyzed the label for it. Now, what can happen is our poster who is getting blocked by the text classifier can take and modify their text so that it reads the same, but the text classifier does not understand what it's actually saying. And so our poster might do things like add extra spaces in between their words that are negative, or add non-English characters in those words as well, in order to cause the text classifier not to be able to recognize these, and instead they become unknown words. And some advantages to these simple changes is they're easy for humans to still be able to read and understand, even though the text classifier cannot. And now these specific examples that are displayed here have already been explored in previous character level attack papers. Another thing someone might do that's trying to bypass the text classifier is rewrite their text vertically, because again, this accomplishes a similar effect where a text classifier is no longer going to view these as the same words because there's all these extra white spaces in how the text classifier will process this text, but humans can still easily read these as their original intended words. And it turns out this has not been explored yet, and thus provides the basis for our research we're presenting today, which is our adversarial attack, Vert Attack. And so the point of Vert Attack is to try and simulate how humans might additionally attack these text classifiers. And so Vert Attack itself can be broken into two main parts, which we'll explore here very briefly. First is the selecting of which word it should change, and then transforming that to the vertical writing. A few other things to note. First of all, black box knowledge is assumed, which it just means that our attacker can query the classifier to get labels and probabilities for feedback, but they have no knowledge of the training data or internal weights. And there's two main goals that Vert Attack will focus on. First is, as we've said, it's trying to bypass that classifier, make a wrong classification. The second, that's equally important, is to maintain that original readability and understanding of the original text for humans, because if it changes the actual meaning of the text, then the attack is also not successful. So it has to keep both of these in mind when it's changing text. And so for word selection, the first thing Vert Attack needs to do is, given the input text, which words in here should it modify such that it'll change the label that's given by the text classifier. And again, the text classifier for a given text will give a label and then the probability for that specific label. And so we, for Vert Attack, adapt a previously adapted strategy called greedy search, also called greedy select before importance score, using some other adversarial word level attacks. And within this greedy search, we remove one word at a time and are checking to see how that affects that target label probability. And what happens then is we simply remove one word here. I just have it crossed out, but it'll be removed from that text. Then that remaining text is set into the text classifier, and the new probability is checked. And we compare this against the original probability of the entire text. And we'll do this for every single word. So I gets put back into the text, and we'll remove, really, in this case, the next word in the sequence. Again, send it through the text classifier and check that probability and compare for the change for the original text. and so on. Next one being hate really was put back in, hate is removed, check, and again, look at that drop in probability there. This is done over and over for every single word in the text, which results in a drop in probability from the original text for every single word that's removed within there. So finally, then the word that is selected is the one that has that highest drop in probability, because this is the word that's the classifier is relying on the most to help it make its classification decision. In this case, hate has a much larger drop than any of the others, so this would be the first one that's chosen to be modified. Now that we have the word chosen, we go to our next step within the attack, which is transforming that word. And as the name implies, Vert Attack, we're rewriting it vertically. And so that's what we do. We follow this algorithm to rewrite the chosen word vertically within the text. And so in this case, hate is rewritten vertically. And again, we can see that we can still read it as humans, but now this would cause the classifier, no matter in its normal pre-processing, not to view this as the word hate, but probably put the A and T and E maybe together and get some other word from that. Another thing we add in, because text isn't infinitely going across on the horizontal plane, is a width constraint to limit how many words are going to be written per line. So for in this case, we'd have 1, 2, 3, 4, 5 words as a width constraint, which means it's only going to have 5 per line, and that's all taken into account in the transformation. And we can make that wider or shorter depending on what kind of website or where we want to put the text. Now we check now this modified text against the classifier again, and we see some change in probability, and we check the label. Now if the label changes from the original target label to another label, then it's considered a successful attack and the attack ends. But if it doesn't, like in this case, the process will continue and we'll choose the next most probable word, the next highest word drop found in that selection step, and modify that. And check that again against the text classifier. And thus the process is repeated over and over until it's able to change that text classifier's label. In this given example, we modify one more word, which then causes the classifier's label to flip to something else, and thus this attack would end, and this would be the resulting text. We test this attack on 5 different common data sets looked at in adversarial attacks, as well as 4 classifiers, different variations of Vert and more advanced Vert variation classifiers. And for each, following previous adversarial attack research, we sample up to 1,000 samples per data set, and at least 3 classifiers are attacked per data set coming from these 4 classifiers. Here are our main results, which we can see in this table here. We see the different data sets mentioned before, the classifiers used for feedback here for how the attack would choose which words and modify them, and then the actual resulting classifiers. And so we look at both when the classifier is the same as the one that we use for feedback, as well as instances where it's different. We find that strong results occur when the classifier that's used for feedback is the same as the classifier used at the end attack. And so we see large drops. For example, here the original accuracy was 94.2, drops all the way down to 4.7. And that's across data sets as well. COLA up 80%, 81% accuracy, drops down to 5.5, similar things for the other data sets as well. And it should be noted that this instance, when the classifier for feedback is the same as the target classifier, this is kind of the standard examination for adversarial attacks. We also see drops when the target classifier is different from the one used from feedback. Not quite as strong the drops, but we still see drops. So for example, again, up in this AG News dataset, Vert is used for feedback, and we can drop Roberta classifier from 94 down to 26 here. And this table over here kind of shows a summary. The top was the same averaged across, and different. So we see again the same has higher drops on average, but we still see strong drops for when the classifiers differ. As noted, it shouldn't just fool the classifier, but it also needs to be understood by humans. And so we also look at a human study, ask humans to label text 100 different ones, and they'll label both ones perturbed and changed by Vert Attack as well as original text. And they're trying to label them as positive or negative text. And we find for the human study that it's a slight drop for Vert Attack text with 77% correctly identified compared to 81, but still a very similar score for these. So this shows that humans are still able to understand these Vert Attack modified text. Now we also investigate defenses against this attack. We first examine simpler white space removal, which is some more, and segmentation, which might be more standard what current systems are already using to have and pre-process text. We also investigate a algorithm which knows what Vert Attack does, so it reverses the entire algorithm of Vert Attack. Now these first ones, for time-wise, we won't go into them, but we find that Vert Attack overall is still successful against these, and we'll quickly go into this reverse algorithm. It turns out when the algorithm knows exactly what Vert Attack is doing and reverses it, it's able to do pretty well on getting the accuracies back up to their original accuracy levels. So we take Vert Attack a step further and say, well, how do we address this sort of defense? What might a logical next step be? And what we do is add in chaff to this text so that if the reverse algorithm tries to reverse it, it's going to have even a harder time finding the original words. And so, for example, here is our original text. Now, what chaff does is rather than always adding white space in between the lines, it has some probability p to add in a random English character. And again, the idea is humans can still read what the original text is, but now when the reverse algorithm is trying to reverse this, it's going to get tripped up on some of these characters within there. And we find with our chaff results, as we increase the chaff, then the probabilities start to return back down to their attack level probabilities. We also, again, ask humans because adding this chaff in can affect that readability. And we see that at least one human are still able to identify the majority of text correctly, although readability is slightly affected with that chaff, which makes sense. That brings us to the end of the presentation. There's lots more analysis against other attacks and things like that within the paper, so I encourage you to check it out. Thank you.